Thanks for taking the time to attend today's webinar about our SolidWorks Plastics engineering software. SolidWorks Plastics is made up of 3 specific bundles for those who are first-time attenders: Plastics Standard, Plastics Professional, and Plastics Premium. We like to bundle our simulation products. Each package provides capabilities that will allow you to avoid problems that can occur associated with part design, mold design, and unwanted effects brought on by the molding process itself, such as warp. We can address all of that. And today's webinar is part 2 of a 3-part series. We will continue our story from last month's webinar using a real-life example of a project I was personally involved with, a near disaster. We're going to take a look at how SolidWorks Plastics Professional can help you design better products and avoid problems later in the production process. So once we get through my little recap of my near disaster story, and it still continues on with our whole 3-part series, I'm going to ask Sashi if he could show us how using the plastics design software available to all of us today, how it can help us avoid problems in the future, especially in the Plastics Professional bundle. Before we get started, due to some time constraints we may run into, I'm going to ask anyone with a question about today's presentation to write us an email that we can answer directly. We will list our contact information for you on our last slide. So with that, let's talk about my experience designing a solar flashlight. Just going to recap this briefly because it's relevant to where we've been and where we're going. A while back, when I was designing products and manufacturing products for people, I was asked from one of my customers to build and design a plastics enclosure for an electronic flashlight with all kinds of bells and whistles. It has a solar panel, as you can see. It had 2 USB ports up in the top that you could plug your devices into to allow anywhere in the world where the sun was out, you could charge your phone or whatever. It was great. It's got a battery inside, circuit boards. It's a great product. And so I took it on. I thought, well, this would be fun. And the guy who asked me to do it was one of my best customers. So I decided to go ahead and start building this product. So next, Sash. So basically what happened was I had 18 weeks to get this product to a trade show where the customer was going to introduce it to the market, try to sell it to disaster relief programs and national security, whatever, Red Cross, anybody who deals with problems. Even out in some of the parts of the country where there is no electricity, if you're mountain climbing, if you're trail biking, whatever, you would always have access to be able to flash the light, use it at night. It has a SOS linking feature. It was pretty good. So it was really, if you look at it, a pretty easy peasy design. Just kind of, I don't know, box full of parts, put them all in an enclosure. So phase 1 was kind of a conceptual design. I sketched it out, gave it a basic look, and then modeled up something that I thought was, pretty appealing, and you could hold it in your hand, it would float. It had a lot of nice features. Anyways, it took me about 2 weeks to do that. Go ahead. And then with a deadline of about 18 weeks out, I had a finished model. I was told to send it to a molder from China, and that they would make the mold and send us back some parts probably within about 8 weeks. So now we're about, keep going, Sash. About 8 weeks for the molder. I get the parts back, and with 6 weeks to go, I still think I'm in pretty good shape. We've got to put this thing together and test it and what have you. And I come to find out that I'm in a little bit of trouble because this thing has sink marks, quite a few sink marks, and it looks awful. And the customer is not happy. So now I've got to figure out what I've got to do to to solve this problem. Here is where the real problem starts. To get rid of those sink marks on the back, I went with the little cross standoffs. And then on the other side, there was a lot of sink marks that I had to make some changes to. That area and that photo right there was just awful looking. So I really had some eyeballs looking at me like, what are we going to do? So my fix for those sink marks was to put those little square indents in there to take the plastic out where it was too thick and kind of give it a uniform wall thickness, which kind of made it look racy, if you will. I don't know, maybe, I don't think anyone realized why I did that, but other than to get rid of the sink marks. But when it was all said and done, it turned out to be pretty good. Go ahead, Sach. But there is one big problem that when I finally, after 5 weeks of reworking this mold to make those changes, I was provided sample parts with a week away. And the bottom line to the story was I was in deep trouble because they had already booked hotels. They booked the space at the show. They printed documentation that didn't look like the parts that were now changed. It was really tense. We finally did deliver these flashlights with about a day or two left before the show, and it turned out okay. But I guess my point here was that it was a living hell worrying about this, that when you do have a problem, and fortunately for me, and we're going to talk about this in a minute, fortunately for me, I only had those small problems of sink marks. I can't imagine the problems I would have had if it was short shotting, if it was having gas traps or burn marks, whatever. The balanced runners didn't work out. So there were a million other problems I could have experienced. I got lucky. Otherwise, I would have been in real trouble. So what it really involves, one more, Sash, is go to the next slide. Yeah. Is molds are expensive. So you really have a couple of things going on here. You have somebody like myself sitting there designing the part, not being able to catch those problems that I experienced, because back then we didn't have the software really to do what we can do today. So I experienced that back and forth, fix the mold, what have you. As you could see, that mold is this is a typical mold, and I wouldn't even consider it a big one. This is what's involved in making a mold. You have injector pins and sliders and springs and sprues, and that doesn't even show you the core and cavity and how complex that can be. It took 5 weeks to modify that mold, which is probably about half the size of the one that we used for the flashlight, to get it to where it could shoot that part again without those sink marks. So it was expensive. It cost us a lot more money to fix it. And it almost killed our whole deal of selling it by not being able to get it to the show. So for those who've never seen a mold, I'm sure most of you have, but this is a very complex instrument. It's very precise. You have to have both halves of those molds touch exactly right to avoid flash and other problems related to making a plastic part. Not an easy endeavor. It sounds easy, looks easy, but it's not. And being able to design that part before sending it off to the mold was one thing. Phase one, that was where we could use plastic standard, and I would welcome to use it if I ever have to do this again. But then it gets into phase two, where someone's got to design and build this mold, and that's what I'm going to have Sashi talk about today. What products do we have in our packages here that can help us avoid problems at this level, the mold design and the manufacturing the mold. So Sash, tell us what you know about this.
Thanks, Bob. Wow, that was quite the adventure that you had there with that plastic part, and
Yep.
a lot of that could have been avoided, was avoided by implementing simulation into the design phase, which is so important these days that that just has to be a part of designing a part. And beyond that, with some of the things that you did in the first webinar, you talked about, will the pot fill? How did it fill? If you can, you might run into some race tracking issues that could cause well lines. And you talked about sink marks, right? How does the pot look? Being that this is it's a visible part, it's a consumer part. It has to look nice, has to look sleek. So these are some of the things that you can capture as part of the plastic standard analysis. But then you have to start thinking beyond that, because we have to manufacture this part in a realistic environment, right? Where you're not just going to be filling the part, not just going to be filling one part, you're going to be filling a multi-cavity, and you might be filling, you might have to add some additional tools for venting. There might be, and you talked about that feature on the back end where it needed inserts. So how do you account for all of these as part of your analysis? And that's kind of where you would upgrade your analysis into the next level, which is what we're going to talk about today, is that plastic professional. So, I took a look at that model that you were using, and I would say you got pretty lucky, because there were some areas that I would have been a little bit concerned about if I didn't run some of that higher end analysis. So just to quickly recap for our attendees today, what really comes as part of our different level of SolidWorks plastics. So a plastic standard gives you that filling analysis, and as part of that filling, it identifies well lines, sink marks, and you can even try different gate locations, multiple gate, and then also traps. Now, once you've identified some of these issues, some of it you can fix by changing the design. The others you have to fix with perhaps manufacturing parameters, and that's where we can step into that plastic professional. So if the part fills for one single unit, great, but will it fill evenly when you have a multi-cavity? What about family parts, left and right? You have to optimize those runners. A lot of times you could experience a lot of shrinkage in that packing phase, which you can identify using that plastic professional. And of course, venting analysis, you want to try to avoid dieseling and things like that. So, you know, the analysis, it always starts with the fill, right? So this is kind of what you went through in that first webinar. You fill the part, you're able to visually see how the part is filling, and as you can see, as the polymer comes together, that's where some of the well lines would be, and you can start to think about some of the air traps and things like that. And then how do you go from there to that next level, that plastic professional? Why would you want to go to that next level, right? So in terms of the software itself, the way we position plastic standard and plastic professional is plastic standard goes in pretty much in line with that filling stage. Everything that you're concerned about in that filling stage can be included as part of that plastic standard setup. And then you have your pack and hold stage as part of the analysis, and what type of results that pack and hold stage gives you. So filling stage, again, well lined, sink marks, air traps. And then when you think about pack and hold, because it has computed that as part of the analysis, it's able to run some venting analysis to see if you need to add certain vents into your molds. Perhaps, uh, again, runner balancing, multi-cavity, insert molding, shrinkage, stress export. And most importantly, a more accurate cycle time, because your entire cycle time goes throughout your filling stage, and it also includes how much time it takes to pack and hold the plastic part, so that it completely solidifies before ejection. So this will give you a more precise cycle time, for perhaps for quoting purposes, or if you are on a short deadline like you did for this example. So let's go ahead and jump right into SolidWorks. So I'm gonna slide my SolidWorks right over here. So this is the part that you looked at in the previous webcast, and a lot of that analysis was focused on that fill setting, right? So if you open up that fill setting here, a lot of these information really comes from that material that you set for this analysis. So I believe the material was an ABS GP22 from BASF, and it will populate a lot of this process parameters for you. So one thing that's really nice about Plastics Professional right out of the gate for fill setting is that it allows you to check this extra option right here, which is venting analysis. So if you have plastic standard today, you will not see this venting analysis check mark right here. So by simply upgrading your analysis, you'll have this option. You can check this option. It's very simple. You just want to include the ambient temperature, and then you would run that fill analysis, and it will give you venting information. So it will give you pressure, and venting pressure and venting temperature. So we'll take a quick look at that right now. So I'm gonna go ahead into my flow results. I'll say read flow. And I'm not going to go over all of these results because you already did that in the previous webcast, but what's additional now is that you have that venting pressure. So you can see, for example, there's a lot of pressure in this area right here. So as part of the analysis, you could add air vents, and then rerun the analysis, and you can see if it reduces that pressure, that high pressure in this area. Because you being like, this is on the outside of that part, and if you have any type of dieseling and there's scuffs marks or burnt marks, it's not going to look nice, right? So we want to make sure this part looks nice and sleek. So that is one way to identify defects, and as part of that venting analysis. And then obviously you also have that venting pressure. So you could have very high temperatures. In this case, the temperature really is not that much difference. The color contours just because there is a difference of 1 Celsius, and so that's not a cause for concern. But if there's a huge discrepancy in terms of temperature here, that's something that you would definitely want to take a closer look at, and identify why there's a very high temperature and in certain areas um, of your mold, of your cavity. So that's all in terms of adding more to just your fill analysis. Right out of the gate, it gives you that one step above what you've already been doing just with that plastic standard analysis. So now let's go ahead and take a look at that pack setting for this analysis. So with Plastic Professional, you will be able to set your your packing process parameter. And first off, it is that pressure holding time, right? So that pressure holding time, you can see it's kind of grayed out here. And the reason why it's grayed out is because the software is going to calculate how long it takes to pack and hold the polymer in the cavity, right? And then it's going to tell you it's 6 seconds or 7 seconds or 10 seconds, which it might be too long. And then it also starts to calculate some pure cooling time, because throughout the process, throughout that fill stage and the packing stage, the part is continuously cooling due to conduction and convection. and the software can actually start to calculate that value as well. Now you can actually put in some hard values for the holding time. Now let's say if you know for a fact that your holding time cannot be more than 6 seconds, you can actually put that in here by just clicking this button, and you can just enter that number in here, and then you can identify if that 6 second holding time is going to cause any issues uh, for that filling process. So that's a really nice way to identify and even give you that inside look into that packing holding phase. And Bob, you of all person would know this, that once the pot once the mold is filled and it's closed, you don't really know what's going on in there until the pot is ejected. Once it's out, you can take a look at the part. It's warped, it's shrinked, there's sink marks. All that is you have to identify post ejection. What the analysis gives you is that inside look, right? So now you can actually see what's going on during that packing phase. Is some of the issues that you're seeing at the ejection phase happening during the packing? So what if it is? Then maybe there's some process parameters that you can change during the packing phase. For example, the pressure, the holding pressure, right? So that's where the pressure profile setting right here comes in. So if you click on this button, it brings up this pressure control. So this pressure control essentially is how much pressure is being applied to the mold as the pod is solidifying, right, from that liquid phase into the solid phase. And a lot of times you have to release some of that pressure to allow for that solidification to happen. So you can actually input that information in here as well, and you can play with these numbers to see if you can possibly reduce that holding time, or you may have to increase that holding time. So you can see here, it's the holding time is we're giving it 10 seconds, and it's going from 80 all the way down to 40 of the injection pressure, and this is inclusive of that filling stage. So just to clarify that this 10 seconds is not just the holding time. This is the filling and holding time included as one, right? So right around that 5 second mark, you can see that 5-6 second mark, we drop that pressure down to 40% of the original injection pressure. And you can also do this using hard numbers, right? So if you change machine pressure control, you can just put in the MPa numbers as well. All right, so right away, now you have full control over your packing phase. So let's go ahead and take a look at some of the results that you can get from out of this pack analysis. So let's see here. Oh, actually, that's in a different configuration. So this is the original analysis. So I'm going to switch this over. So that previous configuration was just the venting analysis with the fill analysis. So I'm just switching it over to a different configuration that has the flow and pack analysis already pre-ran. So we'll take a look at the pack results here. All right. So what some of the results that you can get? Well, first off, pressure at the end of pack. What is the pressure within the mold, within that cavity at the end of pack, right? If it's too high, maybe we need to release a little bit more pressure during that holding phase. Then we also have that volumetric shrinkage at end of pack. So this is very, very important, because if this number there's a huge discrepancy between this number and the volumetric shrinkage at the end of filling stage and after ejection, then there could be some problems during the holding phase that's causing that volumetric shrinkage. So this is something that we've never really been able to do before, is identify at which stage of the injection molding process is contributing most to that shrinkage of the part. Then, of course, some of the other very important results as part of the pack analysis is temperature at post-filling end. So you can see here the temperature, not too bad. Freezing time. So if you have any gate freezing issues, this is where you will see. If, for example, certain areas of the part has frozen beforehand, and it's blocking the flow of the polymer, you'll be able to identify it using this pack analysis results. Residual stress at post-filling end. So this is also very important. So if you have any residual stress, it can contribute towards warping as well as shrinkage. So we can identify if there's a lot of residual stresses within that within the part itself. And then frozen areas at post-filling end. This actually correlates with that freezing time, as I just mentioned. So frozen area actually gives you an instant graphical view if there's any areas that were frozen. And in this part, pretty lucky. Like Bob said, he's pretty lucky. I mean, the pot worked, right? I mean that the mold, I mean the pot filled, no problems, came out perfect, and this results correlates with that. So there's no red. If you see any red, means that there's some freezing that's happening there. So that is the first stage, right? So you have this single part, you've ran the fill analysis, you've gotten some of your results, and then now you've taken it a step further, you've ran that pack analysis, and you've gotten more results to identify, to really understand how, not only how the part, how that cavity is filling, but how that part is going from that liquid form to that solid form, which is going to be your final part. So now we can actually take it a step further, right? So we know for a fact that we are not just going to, mold just this one part, right? This part is this flashlight is an assembly. So there's a top and bottom cover. So this is the bottom cover, and this is actually the top cover, and there's actually a bottom cover. So if I switch over to this other configuration, we can actually see both the covers. And a lot of times when you have covers like this, top and bottom, you may want to mold it as a multi-cavity run, right? And a lot of times, reasons of saving costs, so you don't have to cut two molds, you only have to cut one mold, and for tolerance sakes, and so if you are machining one mold versus two separate molds, you might have less of a tolerance issue there. So there is a huge benefit to doing that. But with this type of mold comes its own set of issues, such as the runners, designing the runners, and knowing how to flow the polymer correctly. So first, let's take a look at how we can actually design runners into this analysis. So I'm going to go into my plastics analysis. And when you have two cavity domains as part of your analysis, it instantly lets you build what is called a runner system. And that's a domain of its own. So you can see here, I've actually just included a very simple runner in here. And really, to design a runner, it's very, very simple. If you go into your part level, all it is it's a 3D sketch. You can see here that I created a 3D sketch. I'm able to include all my dimensions, which I can change, right, depending on the results. I can change the design of my runner very, very quickly because these are just simple sketches. And then I go back into my plastics analysis, and I'm just going to go ahead and edit definition that runner. So you can see that runner, all I'm doing here is I'm just selecting that sketch. So I select the sketch. and then I define what is the initial diameter of that runner and the end diameter of that runner for each sketch entity, right? And towards the end, where your runner is meeting up with your gate location, or sorry, where it's actually being injected into the mold, you might have a taper, where because the point of ejection is smaller, so you can actually include that as a draft, or you can actually just put in hard numbers. So I could have 3 millimeters down to 2 millimeters as part of my runner setup. And just like everything else, if you were in the previous webcast, they talked a little bit about meshing the part. So same thing, runner is a domain, so you have to mesh it. So just in this case, it's just meshed as 10 elements. So that's just a very good round number to use, 10 elements. A lot of times you get very good results using 10 elements. So once I've um, selected the sketches to create the runner system, you can see that it automatically creates that runner system for me. And as opposed to setting up that gate location directly on the part, as you have done in that filling stage, here you actually set that gate location right at the start of your runner. So it actually gives you better cycle time, right? Because there's going to take a little bit of time for the polymer to run through the runners before it actually hits the cavity. So now that cycle time includes all of that. So if you take a look at results, so in this case, again, we're just talking about fill analysis. So as part of Plastic Professional, you can run a fill and pack analysis for a multi-cavity setup like this. So let's go ahead and take a look at how these parts fill. So it's just reading up all the results at this time. Okay. And slow this down a little bit. And let's take a look at the fill. So one thing right away, and I always like to view my filling process slowly and graphically right away, right off the bat after I run the analysis, because it tells a story of its own, right? Right away, I can tell that it's not even. One side is filling much faster than the other side, right? So this side is filling much faster than this side. Now that actually can cause some issues, right? Gate freezing issues. It can cause unevenness with the fill, because the polymer is just going to continuously run through these runners as long as the cavity needs to fill, but then one part's already filled and the other is not filled yet. So this is something that I would be happy to identify in this stage, because now I can fix it, right? One thing that I know from experience is that because these two parts are not symmetrical, the runners cannot be symmetrical, right? Um, in terms of volume, obviously there's some difference in volume. So one cavity might need more polymer than the other. So how do we do that? How do we identify what is the best runner size for the different cavities? Well, we do have a really neat tool within SolidWorks Plastics, which is called, oops, it's not in here. I'm going to have to switch over to my next configuration. It's called runner balancing. And I'll tell you why that it didn't show up in the previous analysis, because this analysis that I did right now that I showed you, I did it with a solid mesh. A solid mesh will give you more accurate results, but then it will take a little bit extra time to run the analysis and solve the analysis. You absolutely want to run your final analysis, the analysis that you're going to be making real engineering decisions on, with a solid mesh. But in terms of things like, let's say, runner balancing, where you're more concerned about the runners as opposed to, specific defects on the part itself, um, you would want to run it as a shell mesh. So by default, SolidWorks Plastics requires you to run runner balancing using shell mesh. And another reason why we require you to run it as a shell mesh is because essentially what happens when you do a runner balancing is that it continuously runs multiple iterations of the fill process until it figures out what's the right size for the runners. And shell mesh runs the analysis much quicker. So if you take a look at right here in the mesh settings, you can see that there is a tool here called runner balancing. So if you click on runner balancing, so give it a second here. We can see that here's your setup, right? So you can see a maximum number of iterations, 20. So this is what I was talking about. So that 20 iterations, actually, it will fill this analysis 20 times. And then it's going to figure out, well, it's not going to do it up to 20. It's going to do it up to 20 times. So it could stop at 5 times or 7 times. The analysis really decides, but basically what it's looking for, it's convergence of what is the best runner balancing size. So you can set the maximum diameter, the minimum diameter, the maximum diameter of the inlet, and the minimum diameter of the inlet as well. And you give the analysis some room here to grow the runner or shrink the runner, depending on what the analysis comes back with, right? So once you've set all of these, very simple to do, you hit calculate and you wait for the results. So I'm going to see here if I have the results. If not, I do have an image of the results that I can also share with you. So let's, oh, actually, you know what? I do have the results. So let me go ahead and go back into that runner balancing. So the results for runner balancing is right within the runner balancing analysis itself. So previously, in the previous analysis, as you've seen, when I set up the runner, I had this as so this runner, and these three sketch entities were just 3 millimeters start and end. There was no tapering. The only taper I had was for these two entities that actually goes into the cavity, into the mold. And this I had a draft of, it goes from 3 millimeters down to 2 millimeters, and it was the same on both ends. So when I select here, show thickness distribution, what this does is you can see here that the analysis has actually changed some of these numbers for me. So now it's no longer 3 and 2. It's now recommending that I bump up these three entities to 5 millimeters. And then in terms of that actual inlet itself, this is 3.5 and this is 2.8. And obviously, you can round these numbers. You can change your analysis to round up this number. So maybe I would do, 3.5 millimeters here, and I would do, 3 millimeters here, and run the analysis and see, what type of results I get, if I'm still getting a lot of race tracking issues, or if I'm getting any type of gate freezing, anything like that. But let me see if I can, yeah, there we go. That's a much better view. So with this results, we can kind of think about this a little bit more. Why is this number much larger than this number? Because we want to allow more polymer to flow here, because when the outlet is bigger, there's more flow rate. So the is an increase of flow rate, so it actually speeds up the velocity of the polymer in this cavity is actually faster than this. So it actually fills up faster. But actually what it's doing is that as this is filling up faster, it's actually evening out the speed of how both of these polymers are filling, so that you get a very even fill, and the cycle time is equivalent, or the fill time is equivalent for both parts. So again, this is a very nice way to identify that. All right, so let's go ahead and see.
Hey, Sash, can I interject something here?
Yeah.
How difficult is it to address this after you find out the part didn't fill? This is a major nightmare, right?
Mm-hmm.
You got to pull this mold apart, redo those runners. Now, I've had this experience, just to share this real quickly, not to interrupt, but there's nothing worse than the look on 5 or 6 guys' faces when they're staring at this mold thinking, I don't know, should we open it up a little bit more, a lot more? Should we, back in the day, we didn't have all the simulation software. It was always a shot in the dark.
Mm-hmm.
Uh, I think it'll feel better if we go to this dimension. Now you shoot it again and it doesn't fix it. Now what? So having this insight, I guess, before you have to take this mold apart, fix it, is where the value is.
Mm-hmm.
But there's nothing worse than looking at a mold and not being absolutely sure that what you're going to do to it is going to fix it.
Right.
Especially when you have a customer looking for his part.
Yeah.
I just wanted to add that in.
No, and actually you bring up a really good point, Bob, because actually you can see in this analysis, I didn't even run the fill analysis. You can see here, there's no results for flow at all, because at this stage I'm focusing on that runner, right? So this is this tool allows you to hone in on areas that you have questions on, right? So if you know that the part's going to fail, but it's not filling correctly because of the runner, I don't need to rerun that fill analysis here. I can just go into my runner balancing tool and run a specific uh, analysis for the runner. And it gives me the results I need. I can make the changes, so I can go back into my family analysis here that I did run, right? The flow analysis, and then I can make my changes to my runner. Actually, in fact, the runner balancing changes the number for you, but it obviously gives you, because it's mathematical, it gives you those numbers which are not so pretty, right? 3.8735, whatever. So you can actually change that, right, to round up the numbers and then rerun the analysis, and right, that kind of builds your confidence that you are going to get a much better fill when you run this, on the floor. So with that said, I just wanted to hop out of SolidWorks and actually talk about a real world example. Well, your example was real world as well, but again, you didn't run into that any issues, when you ran the family part and some of that. But here is an example that we did with the fine folks at UMass Lowell, which is really the one of the best universities here in the United States for plastics engineering, on actually running into some fill issues because of uneven runners and things like that. So the analysis was done on a Sumimoto injection molding machine. So we actually ran the analysis and then ran a real run on the injection molding machine. Pressures taken from the machine display, and clamp forces estimated from machine display as well. But the thing is, a lot of this information we can input into the analysis to see if it correlates correctly. So the material, polypropylene, family mold imbalance, and let's take a look at some of the results. So they ran the analysis. These were some of the results, and oh man, thank God this is a test setting. In real world, I remember Bob, when I was doing some of this stuff as a real engineer, and if it came out like this, I would be updating my resume. That's for sure. So we definitely want to try to avoid these types of problems as much as possible. So we really focus in on three of these shots. So obviously you can see there's a shot here. So the first one, it's shot on both units, both ends, both cavities. On the second, that it filled in a little bit more, but still not completely filled on both ends. On the third run, one of the sides did fill completely, but the other did not. So here's an example of that imbalance that I just showed in SolidWorks Plastics, which we could have fixed with that runner balancing. So here's the first example, which correlated with the results that we got. You can see that it is almost exact in this case. So we ran the analysis, 20 cc dosage volume, filling time 0.4 seconds, and this was the results that we got on the analysis. And this was the the shot results, the short shot, and here was the actual part itself. Here's the second run that we did. Again, very close in terms of results, almost exact in this case. And then here's the third run. Actually, looking at it from a different angle, it didn't actually fill all the way towards the end, and the analysis was able to catch that as well. And this is, that's the level of accuracy that we can catch. You always have to think about, in terms of the software is built to fill the part, right? Its task is to fill the part. So it's going to try its best to fill the part. And if it's not filling the part, or even if it does fill graphically in the software, but it's telling you that it had a lot of uh, um, it was very difficult to fill the results. There's actually results that gives you how easy, it's called ease of fill. So if it says that it is very difficult to fill from a software perspective, then chances are in reality it's not going to fill all the way. So here's an animation of that filling. You can see how it slows down at the end. So if it's struggling to fill, it will come almost to a dead stop. And again, right, the software's goal is to try to fill it. And it's going to keep pushing and pushing and try to fill it. But if it's struggling, it's going to say that the ease of fill is very difficult. And I almost bet you that in reality, it's not going to fill. So here are some results, and all of these graphs were extracted from SolidWorks Plastics. So a lot of the results that I've just shown is graphical, but keep in mind that if you want to get into the actual numbers and do some comparison, whether you're a plastic designer or you are actually working in a mold house, some of these numbers matter, because even in the design environment, if you know more, you have more control over the entire process. So in terms of max pressure simulation, 48 MPa is what the max pressure results that we got. The test, the actual physical test was 50.9 MPa. So obviously some slight discrepancy there, but almost exact. The other thing is packing. So we talked about packing as part of the plastic professional. So we did we released that packing pressure a little bit here, that holding pressure I talked about earlier. So you can change that number. So here that number was set to 43, and you're able to get some insight information. What about gate freezing, right? So we didn't run into any gate freezing issues with the example I showed, but if you do, you can actually extract some of that information graph from in a graph format, and you can do a comparison with the glass transition temperature, and you can see that if it's gone below or above that glass transition temperature, at which point you can induce that gate freezing problem. So a lot of this you can predict just from the virtual simulation itself. And then part weight. Imagine being able to guess the final part weight from the analysis itself, and how the part weight changes as the cavity is filling. So um, when you're designing a part in SolidWorks, you're designing it, usually what we call it is zero base, right? So you don't include any tolerances, you don't include any shrinkage, you just design it to spec. And then when you run the analysis, if you're predicting some shrinkage, let's say if you're predicting 3% shrinkage, you would just scale that part up by 3% using SolidWorks scale tool in the features. And then when it scales back down, you can check to see if that part weight correlates with what you are supposedly expecting the part weight to be, and if the size of that final part that comes out after that injection molding analysis is correct, right? If it's shrunk down to the right size. And again, here you can predict some of that gate freeze, that gate freeze prediction. The time here, 6 seconds. Test was between 4 to 6 seconds. So to kind of summarize, we have about 7 minutes here. So just to summarize this presentation, when you go from plastic standard to that plastic professional, you're not just upgrading your software, you're really upgrading your ability to do more and get more out of the analysis, right? So it's really the term here, upgrading your analysis, upgrading your engineering team, getting more out of the analysis. So in a plastic standard environment, that filling stage, some of the questions you have and some of the questions you can answer is, will it fill? Obviously, if it doesn't fill, all bets are off. Forget about it, right? But once it's filled, then you talk about defects. Can I have a better gate location to maybe avoid race tracking issues, to avoid air traps in bad areas? Structurally, is it going to work? If I have my polymer coming together in a critical area, because weld lines, knit lines it can cause structural problems. Maybe I want to change my gate location. I'll be able to do all of that in that plastic standard stage. And then obviously, can the design be optimized, right? So what we've always advocated is that you're running this analysis not just to figure out what's happening at the back end in the manufacturing end. You're running this analysis so that you can design better parts, right? Design better plastic parts from the get-go. So I can run the analysis, and if I can change my design so that I can reduce I can have one less mold rework. Imagine, the time and all that savings from just making certain design changes, removing, adding features and things like that. Then once you've identified all of these in that filling stage, you upgrade your analysis. Think about what else can I get out of the analysis? Well, one thing is venting. Do I need venting? And if you do, typically to avoid dieseling, and you can add vents as part of your analysis, and you can see if if you are reducing vent pressure and venting temperature and things of that nature. You can start to identify if there's any defects that is happening during the pack and hold stage, right? So something that we've never been able to do in the physical stage, but now we can try to figure out that, hey, maybe we are holding the molds, that holding pressure is too much, and that's what's causing the problem. So maybe we need to release that a little bit more. um, Plastic Professional also gives you the ability to do a multi-cavity fill, and obviously that runner design optimization. If you are running a different, like a left and right part in this case. And obviously the big question here, what is the total cycle time? We need to include everything. We need to include the filling, the packing, the holding, the freezing, all of that, to really understand how much time it's going to take for that part to eject out of that injection molding machine. And that's when you can make real decisions, not just for that plastic part, but for your entire engineering process, right? Because this is just one part of your entire engineering process. So if you can estimate how much time it's going to take to get these parts out, then you can start making the right decisions for the next stage, right? For packaging and shipping and all that other things that's part of your day to day.